In this video, we're going to talk about an algorithm for computing the change of basis matrix when we're working in Rn. Okay, so remember the context with the change of basis is we have two bases for the same vector space. So I'm going to call them B and C, and let's just say that these are both bases of Rn, which means they each have n vectors. So let's remind ourselves that if we want to find the coordinate vector of B1 relative to the basis C, what we need to do is we form an augmented matrix where we take the vectors and the basis for C, so C1 up until Cn, they're on the left-hand side of my augmented bar. And then because we're finding the coordinate vector of B1 here, B1 is what goes on the right-hand side. And the reason why we're forming this augmented matrix is when we're trying to find this coordinate vector of B1 relative to C, what we're trying to do really is we're trying to write what B1 is as a linear combination of the vectors in C. So as x1 times some vector C1 plus dot 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 plus xn times Cn. And I want to know what these weights are, x1 up until xn. And the way I do that is I form this augmented matrix of the vector C1 on the left-hand side of the bar, and then B1 on the right-hand side. Okay, but what we noticed in the last video was, to get our change of basis matrix, we had to solve this augmented system for every single vector in the basis B. So we had to do it for B1 and B2, and then if there are more vectors, we have to keep going, eventually until we get to Bn. But the process of row reduction is exactly the same on the left-hand side, because I always have the same vectors on the left-hand side. So what if I could do that row reduction all at once? And that's what this algorithm is going to be all about. So the algorithm says, well, let's form a matrix, or on the left-hand side, I just put C1 to Cn, the vectors. But on the right-hand side, I will put all the Bi vectors. So B1, dot, 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 up until Bn. So when I do that, when I row reduce this, the left-hand side is going to become In, because the C's form a basis. So they'll have a pivot in every row and column, so they should reduce to In. And on the right-hand side, each of these vectors individually, each of these columns, will row reduce to a coordinate vector like this. So what will end up happening is I will get the change of basis matrix here. Because remember, the columns of the change of basis matrix were these coordinate vectors that look like this. Okay, so let's do this with an example. It's going to be the same example that we've been working with in the last couple of videos. And I want to work with the same example just to make sure that we are getting the same thing when we find this change of basis matrix in other ways. Okay, so I'm working in R2. I got these bases B and C, and I want to find this change of basis matrix using this row reduction algorithm. So the algorithm says, well, what I should do is I should form this augmented matrix where I put the C's on the left-hand side. So I'll put -1, -6, -1, -2 on the left-hand side of the augmented bar. And then I put the B vectors, B1 and B2, on the right-hand side. So I'll put 1, 1, and then 2, 1. And then we row reduce this to make the left-hand side become the identity. It's kind of like, it's similar to finding an inverse that way, where we set up this augmented matrix and we're trying to make the left-hand side become the identity. Okay, so this time I'm actually going to carry through the row operations just so we can see it. Okay, so what we will do is I want to zero out this -6 first. So I'll do -6 times row 1 and add that to row 2 and plug that into row 2. So doing that, the first row stays the same as -1, -1, augmented with 1, 2, but the next row is going to change. So when I multiply -1 by -6, I'll get +6, and I add that to -6, I'll get 0. And then when I multiply this -1 by -6, I'll get a +6, and I add that to -2, and I get 4. Multiplying this 1 by -6, I get -6, and add that to 1, and I get -5. Multiplying the 2 by -6, I get -12, and adding that to 1, we get -11. Okay. All right, so at this point I have it in echelon form, but not reduced echelon form like I need. So I know where the pivots are. I know the -1 is a pivot. I know the 4 is a pivot. But to put it in reduced form, I know I have to make the pivots become 1. So let's multiply the first row by -1 and insert that into the first row. And the second row, let's multiply by 1/4. It'll introduce fractions, but there isn't really a way around that here. I'll need to roll up our sleeves and deal with the fractions. It's okay. So the first row, multiplying through by negative, I'll get 1, 1, augmented with -1, -2. And then with the second row, when I multiply by 1/4, I'll get 0, 1, -5/4, and -11/4. And we are one row operation away. Now I want to zero out the things above the pivots. So I would do row 1 minus row 2 and insert that into row 1. So the second row is going to stay the same. 0, 1 augmented with -5/4 and what was it? -11/4. On the top, I subtract the second row from the first. So I'll get 1, 0, -1 minus -5/4 is going to give me +1/4. And then -2 minus -11/4 will give me +3/4 if I get a common denominator and whatnot. Okay, so this matrix on the right-hand side of the augmented bar, now that the left-hand side is the identity, the right-hand side is supposed to be my change of basis matrix. This is PB, arrow to C, B changing to C. Okay, so let's just write that down on its own. So my change of basis matrix, P, B going to C, is 1/4, -5/4, 3/4, and -11/4. And that's my change of basis matrix. And if you refer back to how we got this in the previous video, let me just show that in the notes. So in the notes, in the previous video, we got the same thing. But notice that in the last video when we did this, we went about and set up 2 different augmented matrices, one for each of the basis vectors in B. So the nice part about this algorithm is it lets me do that row reduction all at once. Okay, so one key thing that I want to note about this is all the computations I've done so far have been, well, what if I want to change my basis from B to C? But what if I wanted to do the opposite? What if I wanted to form the change of basis matrix that takes C coordinates and turns them into B coordinates? Well, just like in section 4.4, it's going to be the inverse of this matrix. So it's the inverse of this B to C matrix. Okay, so what I want to end this video with is just recapping all the ways that we have to find this change of basis matrix. So the first way that we talked about was our definition of the change of basis matrix, which was you took all of the BI's, all the basis vectors in the basis B, and you found their C coordinate vectors, and you wrote them as columns in a matrix. That was the definition. We talked about that in the last video. So this was last video. In this video, we talked about our algorithm, where we took the basis vectors of C on the left-hand side of the augmented bar, the basis vectors of B on the right-hand side, and then when you row reduce it, the left-hand side will become the identity, and whatever you get on the right-hand side, well, that's your change of basis matrix. That's what we just talked about. And there was one other way that I mentioned in the last video, very briefly. The last video, we actually mentioned this third one before the first one. The formula here was, it was P C inverse times PB, where these matrices are matrices from section 4.4. Remember from section 4.4 that PB, for example, is the matrix that you get when you take the basis vectors of B, so B1 up until Bn, and you just write them as the columns. So in the same sort of way, PC would be the matrix that has C1 up until Cn as the columns. So it's not totally trivial to use this form, even though looking at it might be like, wait, doesn't this look like the simplest? The issue with this form is we would need to figure out what PC inverse is. And finding the inverse takes work. So that's why 3 isn't necessarily the easiest out of these. In fact, I would actually say the first 2 are usually what are most commonly used.